Welcome to the chapter on the fetch and decode stages. So in this chapter, we will study all about the fetch logic, in particular the branch prediction logic, and then discuss some decode time optimizations that are typically done mostly in CISC processors to the amount of substantially increase the performance as well as make it easier to process the instructions in other stages of the pipeline. The basic background required to understand this chapter, well, we need three things. The first is the understanding of basic bits and Boolean logic. The second is, so this is the third chapter. The second chapter was on out of order pipelines. So the motivation part at least. So the need for branch prediction should be clear and why we need an accuracy which is more than 98%. That should be clear. And the viewers of this video should be reasonably aware of RISC and CISC ISAs. What are their trade-offs, their advantages, the typical formats, and so on. So for the required background, viewers can look at my earlier book, Computer Organization and Architecture, published by McGraw-Hill in 2015. So a link is given over here. So there are YouTube videos as well for all of these topics. So I would urge the viewers to kindly take a look at these topics before proceeding forward, because the material in this lecture set heavily depends on these three topics. So any viewer has to be very thorough with these. So first, a brief background. Let us look at the relevant part of the pipeline that discusses the fetch logic. So the crux of the key state element that captures the fetch logic is the program counter, the PC. This points to the next instruction that needs to be fetched from the iCache. So in a RISC instruction set, the size of each instruction is fixed. It is typically either 4 bytes or 8 bytes. So for the sake of simplicity, let's assume it is 4 bytes. So then in this case, the addresses would be like this: PC, PC plus 4, PC plus 8, and so on. So if we have a fetch width that is more than 1, for example, if we fetch, let's say, 2 or 3 or 4 instructions per cycle, then what we can actually do is that we can take multiple addresses, which is essentially PC plus PC, PC plus 4, PC plus 8, and so on, and fetch them from the iCache. The instructions can then be sent to the decoder, which will decode the instructions. Then the decoded instructions will be put in the relevant instruction packets. So what exactly is decoding? Well, an instruction can be considered as a compressed bundle of information. And so a lot of fields are kind of compressed within the instruction. So all of these need to be expanded such that it is much easier to process the instruction in subsequent stages of the pipeline. So what we do is that we take a instruction in a compressed format. So it is not compressed in the typical compression sense, but it is just that we use as few bits as possible to represent information. So a lot of this is expanded. For example, instructions can embed an immediate. An immediate is a constant in computer architecture in parlance. So the immediate can, let's say, be 16 bits. So a 16-bit immediate is expanded to a 32-bit immediate. So all of this process of expansion is done within a decoder. So the expanded instruction is called the instruction packet, which of course contains all its fields and all other pieces of information that are required to process the instruction in the subsequent stages of the pipeline. This is the instruction packet. So of course, if you are reading 4 instructions simultaneously, let's say from these 4 addresses, then we decode all 4 of them in parallel. So we have 4 parallel decoders. and we create 4 instruction packets that are sent down the pipeline. So this is somewhat a simplistic idealized view of the fetch process. Branches actually can cause problems, and a lot of serious problems, in the sense that they make the control flow deviate. So the addresses, instead of being as well behaved as PC, PC plus 4, PC plus 8 and so on, can actually, if this is a branch, then it can branch to a separate address and we need to fetch from there. So this issue will be there. And so if you are fetching 4 instructions at the same time, well, any subset of them can be branches. And so it is the job of the branch prediction and fetch logic to essentially predict both the direction of the branches as well as the target and fetch instructions from there and kind of give us as many instructions from the correct path as possible, such that we can sustain a high fetch bandwidth. So the key summary from this slide is that we need as many instructions right from the correct path as possible. So recall that we had discussed what is the correct path and what is the wrong path in the previous slide set. So the correct path is basically the correct branch path. So from the correct branch path, we need to, this means predict branches correctly and fetch as many instructions as we can, such that we can supply as many instructions as possible in parallel, of course, to the rest of the pipeline. Because the fetch is like the head of the pipeline. So the fetch is slow, the entire pipeline is slow, right? So the fetch is a bottleneck, and if let's say the fetch process is slow, the entire pipeline, even if there is a high degree of high instruction level parallelism, it will not be able to leverage that, mainly because we are not fetching as many instructions as we can execute in parallel. So we need a high bandwidth fetch unit, right? So the key over here, we don't really care about latency, but what we really care about is high bandwidth. All right. So let us look at a simple fetch unit that fetches a single instruction per cycle. So this will be our first example, and then we will gradually complicate this. So what happens is that when you are fetching the ith instruction, we have, what do we have? Well, we only have its program counter, and on the basis of that, we give the program counter to the instruction cache. The instruction cache sees the program counter and fetches the ith instruction. So the ith instruction, mind you, we have not seen it, right? So we are only fetching its, we know its address, we are fetching its contents, but we have not seen it and we have clearly not decoded it. So we are not aware at this specific point of time, which means in this cycle, we are not aware whether it is a branch or not, right? So nevertheless, if we want to fetch the I plus 1th instruction in the next clock cycle, well, then we will have to predict many things, but we will definitely have to predict that after the ith instruction, what is the I plus 1th instruction. If it's a branch, well, we need to predict its outcome and target, and I plus 1th instruction will be the target. Otherwise, if it's not a branch, it is simply PC plus 4, right? That's the address. The same holds for the I plus 1th instruction also. We don't have enough time to see it, right? The moment we are fetching it, we need to calculate the address of the I plus 2th instruction. So we essentially need to predict what will it be, right? So to predict the I plus 2th instruction, well, the I plus 1th instruction, we'll have to, if it's a branch, we'll have to predict its outcome and target. And if it's not, well, in this case, it's again the PC of this instruction plus 4. So on and so forth, we need to proceed. So the most important point that is kind of coming out from this slide in big bold letters is that there is absolutely no time to look at an instruction, right? So we cannot look at an instruction means look at the instruction's contents. There is no time to look at it. We simply know its program counter. On the basis of that, we need to predict the next instruction. And if the current instruction is a branch, that will end up meaning that we need to do a branch prediction. Let us now look at a more complicated version of the previous slide. So in the previous slide, we are fetching one instruction per cycle. In this slide, we will fetch 4 instructions per cycle. So let us consider the first cycle. So assume that we are fetching 4 instructions and we know somehow, we will see how, that these 4 instructions are on the correct path, right? So let's say we know with high likelihood that they are on the correct path. Now the question is that we need to predict the addresses of the next 4 instructions. So the operative part of this discussion is, let us look at the last instruction in this bundle of 4 instructions. Let the program counter of the last instruction be PC. So what we need to do is that in the current cycle, since we know the 4 instructions and their program counters, we need to predict the first instruction in the next bundle. This can either be PC plus 4, or if this instruction is a branch, it can be its branch target. Then we need to predict the next one, the next instruction, and the next. Alright. So we essentially need to predict these 4 instructions, right, on the basis of the program counter of the last instruction of the current bundle. There are numerous complexities in this. This is not easy. The reason it is not easy is because what we have essentially with us is that we have one program counter. This can either be pointing to a regular instruction or a branch. Regardless of whatever it points to, the instruction that succeeds it on the correct path can again be a regular instruction or a branch. Then that instruction can again be regular or a branch, right? So on and so forth. So essentially we are looking at, so let's say if I were to consider these 4 instructions, we can think of them as kind of a multi-way branch, in the sense that there can be multiple branch instructions within them, and so this as far as we are concerned, so which 4 instructions are these? They are essentially these 4. So these 4 instructions can have several branch statements within them, and thus numerous targets are possible, numerous correct paths are possible, and instead of making one prediction in a cycle, we actually need to make 4 predictions. On a similar line, we're using a similar logic. Once we have 4 correct instructions in this cycle, we again need to predict the next 4 instructions on the correct path for the next cycle. So this clearly entails having multiple branch predictors, making multiple predictions per cycle, and still ensuring that we are able to ensure a fetch bandwidth of 4, and those 4 instructions are on the correct path, right? So on the correct path, of course, that we'll get to know later, but as far as we are concerned from a prediction point of view, with a very high likelihood, they are on the correct path. So as you can see, fetching one instruction at a time or fetching 4 at a time is conceptually similar, but the only difference is that if you are fetching 1 at a time, then it is easy because you have 2 possible outcomes, right? It is either PC plus 4 or the target. But if you are, let's say, predicting 2 instructions at a time, then there are numerous options actually. If this is PC, this can be PC plus 4, and the final instruction after that can be PC plus 8, or we can go to the branch target over here, and again one option can be, it can be either the target plus 4, or this can be a branch, and we can go to the branch target of that. So what we see is that we have numerous options. So this is why it's called a multi-way branch when we are considering predicting branches for a bundle of more than one instruction, and this is clearly complicated. This complexity is shown in this slide, where if we see that if we have a bundle of 4 instructions with one branch, this is relatively easy to predict. But if we have 2 branches, it becomes much harder because the program counters of these instructions is dependent on the prediction of this. So this kind of becomes a sequential process, and if we can have even more branches, so that will create more difficulty in terms of doing the prediction, right? So basically, as far as we are concerned in a bundle, if I were to look at the instruction that will just succeed this bundle, we don't have 2 options. So in fact we have many options, right? So even though we start at one point, which is maybe the starting PC of this bundle, right? So even though this is the starting PC, but if I were to look at the instruction that will just succeed the bundle, we actually have a multiplicity of options, many options. Hence, such a bundle with multiple branches is called a multi-way branch, and we'll be using this term multi-way branch reasonably frequently in our discussion in chapter 5. This is an important concept. All right. So what is the summary up till now? Well, the summary up till now is, if I were to kind of summarize the main points. The first is we do not have time, no time to we have no time to look at the instruction. The only thing we can look at is its PC, right? That's the only thing we know. Furthermore, if we want to predict, if we want a fetch bandwidth, a fetch width, so let's call it a fetch width, if we want it to be greater than 1, we are essentially looking at a multi-way branch, where for the bundle as a whole there can be multiple targets, right? Because the bundle can have multiple branches within it. All of these branches have to be predicted correctly, and we will have to find the final correct path, which is hard. So which, a single branch prediction as it is hard, but doing multiple branch predictions is even harder. So this is where the role of a smart compiler comes in. It should ideally generate code such that branches are placed relatively far apart, such that if I were to fetch 4 instructions or 4 contiguous instructions on the correct path, there will be desirably at the most 1 branch. So this will reduce the load on the branch predictor and allow us to design simpler systems, right? As opposed to this multi-way branch scenario. Nevertheless, what we will concern ourselves in this chapter is, given a branch instruction, how do I predict several things, which are predict if an instruction is a branch or not is the first thing that we need to do. Because given an instruction, as I have said, we have not seen it. We have only seen its program counter address. We need to predict in the first place whether it is a branch or not, right? If it's a regular instruction, we are fine. The next instruction will be PC plus 4. If it is a branch, which is 2, we need to predict its direction, which is either taken or not taken. Then we need to predict its target, right? If it is a taken branch, that is, right? If it is not taken, no issue. But if it is a taken branch, we need to predict the target of the branch. So as we see, we have 3 different separate problems over here. Predict if an instruction is a branch or not, problem 1. Problem 2, if it's a branch, predict if it's taken or not taken. Problem 3, if it's taken, predict its target. So we create a black box predictor, which given a program counter just returns its prediction, which can very well be the target of the branch. So now let us come to the contents of this chapter. So we will predict first the instruction type. What kind of an instruction is it? Is it a branch, a non-branch? If it's a branch, what kind of branch? Then we will predict the branch outcome. Then we'll predict the branch target. And finally, we will discuss some decode time optimizations. So now let us come back to our discussion. Given a program counter, the status of the instruction, whether it's a branch or not, this does not change, right? So this is kind of hardwired in the program, that because while we are running the program is not changing. So given a program counter, the status of an instruction never changes. Can we use this information? Well, yes. So what is the approach? The approach is that the last time that we had seen a branch, we remember its PC, right? So whenever we see a branch, we remember its program counter. The next time we see a program counter, we essentially check to see if we have seen it before. If we have seen it before, so we essentially have some sort of a memory, some sort of a remembrance, and we try to see whether it's an unconditional branch, right? Whether it's a conditional branch, which means it depends on the result of a previous compare instruction, whether it's a function call, whether it's a return statement, right? And of course, the fifth category, which I'm not mentioning, which is rather obvious, is whether it's a non-branch. So essentially, we'll have these 5 categories, and for these 5 categories, we essentially need ceiling of bits, which is 3 bits, to represent what is the type of the instruction. All right. So what's the summary again? The summary is we do not have the time to actually look at the contents of the instruction. We simply have access to its program counter address. That's it, nothing else. On the basis of that, we need to predict whether it's a branch or not. If it's a branch, what kind? If we have to do that, we will have to remember the last time the last time we had seen this PC, what was the type of the instruction, and use this memory for prediction. How do we make a hardware structure to remember? Well, it's very easy. So kindly take a look at this structure with a lot of attention. We'll be using this structure over and over and over again for all kinds of predictions throughout the book. So let us consider a program counter address. So we have made our life easy. We are considering a 32-bit program counter. In most modern processors, it is actually 64 bits, but we just want to make our life easy. You can very well replace 32 with 64, it will not cause a difference. Also, one more thing in modern processors is that program counters are typically aligned to 4-byte boundaries, in the sense that they cannot take an arbitrary value, but they typically take values 0, 4, 8, 12, 16 and so on. So this is the case, but we will not use this assumption. Well, why? In the interest of simplicity, we will not use this assumption, even though you should know it does happen. So we will make a somewhat simple assumption just for the sake of easier explanation, which will assume that the program counter addresses can be rather arbitrary, in the sense that they will not be aligned to 4-byte boundaries. Alright, even though in most actual systems, practical systems, they often are aligned. And in our case, if you were to consider that, then anything aligned to a 4-byte boundary, the last 2 bits will be 0 and 0. But let's, as I said, for the sake of simplicity, avoid that. Alright, but you know, whenever a branch predictor is practically being implemented, this should always be kept in mind, that alignment of the PCs to either a 4 byte or 8 byte boundary is important. Nevertheless, let's proceed with a somewhat simplistic assumption. So what we do is we take a look at the n least significant bits. I will discuss why it is the least significant bits in 1 second. So then if I take these n bits, well then there are 2 to the power n combinations. So we have a small table with 2 to the power n entries. And so these n bits will uniquely map to one of the locations within this table. This table, as we discussed, will contain the status, the type of the instruction. We will simply read it from there. Let us call this table the instruction status table, the IST, which of course is a temporary placeholder because later we will add more information to this and we will actually call it the BTB. But till we introduce the term BTB, kindly hang on to the term IST, and once you are introduced the term BTB, you can discard this term. So what is the crux? Well, the crux is we take the n least significant bits, use it to address a table which has 2 to the power n entries. Alright. So now let us see what are the potential problems with this design. What is good with this design is that we can quickly map the program counter to one entry within a table, find out the last time we had encountered this program counter, what was the status, the type of the instruction, and read it. Right, so this is the basic method of operation, where essentially we see a branch instruction, we see its PC, we access the entry in the table. When we are seeing it, we record the branch type, and when we see an instruction at fetch time, so this will of course happen at execute time when we know that an instruction is a branch, or maybe at decode time also, doesn't matter. But when we see an instruction and we don't know it's a branch or not, we check the corresponding entry of the table and we read the type. So the question now arises, so you'll have many of these food for thought burgers throughout the discussion. So why do we choose the n least significant bits, and why not, let's say, the n most significant bits, or maybe n bits in the middle, right? So this has something to do with what is called aliasing, which we will discuss in the next few slides. So if we choose the least significant 10 bits of the PC address, we'll have 1024 entries in the IST. So the first question is that why not use the entire 32 bits? Why just the 10 least significant bits, right? Where n is equal to 10. Why just these bits? Why not all of it? Well, if we have a 2 to the power 32 entry table, it will be very large. So how much is 2 to the power 32 exactly? It is 4 billion roughly. Okay, it's roughly 4 billion entries. And 4 billion is too high a number, too large a number, and we simply don't have the space within the chip to store that many entries. So it is too big, too slow, too much of power, too much of area. So from all of these resource considerations, we need to manage with a significantly smaller table. Hence, we choose a table with 1024 entries as the IST, which is something that we can afford. So the primary problem that will happen with this table, which also takes us back to why we chose the least significant bits and why not any other bits, is basically that it is possible for two instructions. Say this is a PC of 1. It is possible for two instructions to actually share the n least significant bits, right? So this is very well possible. One of the bits, let's say over here, would differ, but the n least significant bits will be common. If these bits are common, they will actually map to the same entry in this table. All right. So if they map to the same entry, what will happen is it is possible that one of them is a branch, one of them is a non-branch, right? So then what will happen is we'll have destructive interference in the sense that if, let's say, the non-branch instruction had come the previous time and now we fetch a branch, we will still predict it to be a non-branch because this is what this entry will contain, and we'll make a mistake. So then when we see the status of this instruction, we'll again convert it back to branch, but next time a non-branch may come, it will read the status as branch, it will again make a mistake, it will again change the status to non-branch. If, let's say, the non-branch instruction keeps getting fetched, there's no problem, but the moment we fetch the branch instruction that maps to the same location, we'll again make a mistake. So this is known as aliasing, or this is known as aliasing or destructive interference. Right? So with destructive interference, what happens? So this is a problem primarily because we have a small finite size table. We are not using all 32 bits. Instead, we are only using 10 bits, right? This is exactly why we have destructive interference, because of this. Now let us answer the question, why are we using the least significant bits and not the most significant bits? So the idea behind the least significant bits is that you consider a set of numbers. So you consider, let's say you want to count from 1 to 100, and let's say consider some point in the middle, 27, 28, 29, 30, 31, 32. Which bit changes more, the one at the units place or one at the tens place? Clearly the bit at the units place is something that changes more, and it is something that I would say is more random. If of course I'm accessing, so assume that I'm accessing numbers between 11 and 99 at random, then what will happen, just extend the logic from this counting example, you will find that the digit at the units place changes far more frequently, and there is much more diversity here as compared to the digit at the tens place, which means that if I were to just consider the least significant bits, I would see much more diversity, I would see much more randomness as compared to the most significant bits. As compared to bits over here, if I consider the least significant bits, I'll see a much more uniform spread, right? So I'll see much more randomness. Now let us come to the next important properties of two properties of a program, spatial and temporal locality. Where spatial locality is that if I have accessed one address, I will access some other address nearby very soon. And temporal locality is I tend to access the same data or same instruction over and over again. So if I were to combine both of these and I would look at programs that, let's say, use loops or something, and since I'm looking at instructions, well, the typical control flow would be I go down the loop, down, 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 again come up, down, 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 again come up. And a program spends most of its time, roughly 90% of the time, in loops, right? So that's the reason there's a lot of locality. So within a small region, you will see most of the diversity in the least significant bits, and the most significant bits for a small region will roughly remain the same. So if I use the most significant bits to address this table, it is possible that most of the instructions that will actually map to the same entry, and we'll have a massive amount of destructive interference, right? Massive amount of aliasing. So if I use the MSBs, the aliasing that I will actually see, right, which is entries, instructions mapping to the same entry, will be very high. As compared to this, if I use the least significant bits, combining this with the fact that programs have spatial temporal locality and most of the randomness is seen towards the lower bits, right? we will see a significantly reduced aliasing, right? So let us say it is reduced. So this is good for us. It will increase the accuracy of this process. So as we have discussed, branch aliasing is a major issue. It is possible that two branches map to the same entry, two non-branches map to the same entry, or a branch and a non-branch map to the same entry. So given the fact that we are only remembering what is it that we had seen last time, and based on that we are predicting what it is most likely this time, aliasing will cause an issue. So there is thus a need for disambiguation. So disambiguation is one of the solutions to fight aliasing, right? So ambiguate is to complicate, complicate, confuse. Disambiguate is to kind of uncomplicate and unconfuse, if there is such a word. So if I were to disambiguate, what do? I augment each entry of the IST with additional information, extra information. So what we need to do is that the primary confusion that actually arises over here is because of the fact that we are using the lower n bits, and the upper 32 minus n bits, they are not being used. So it is possible that two addresses have the lower n bits in common, but the upper 32 minus n bits are not common. So we follow the same procedure, which is that we use the lower n bits to actually address this table of 2 to the power n entries. However, in each entry, along with storing the branch type, which is a small, as I said, a 3-bit field, right? What we do is that we additionally store these 32 minus n bits, right? So these 32 minus n bits are stored here. So then whenever we are trying to predict for a given program counter, we access the entry, check if the remaining bits match or not. So these remaining bits are known as a tag. So we check if the 32 minus n bits match or not. So if they match, we are sure that this entry is actually not the entry of some other branch. It is the entry for this branch, right? So we are sure that the entire PC matches. So n bits of course match because we come here, and the 32 minus n bits match because we store them over here. So once all of them match, we have of course taken destructive aliasing out of the picture, and destructive interference out of the picture, and then we simply read out the branch type. So instead of a thin table, this kind of becomes a fatter table because per entry we are storing more bits. But the advantage is that we are avoiding aliasing to a large extent. So of course here a lot of innovations are possible. If let's say this is n is 10 bits, then the tag will be 22 bits. But we can maybe, instead of saving 22, we can maybe, let's say, save just 10 bits. So what will then happen is that the possibility of aliasing will still be there. However, it will get substantially reduced. And what will we gain? Well, we will gain storage space over here, or this table will be smaller. So then what does this give us? Well, it gives us a smaller table. Sorry, it gives us a larger table at the cost of better accuracy. It also tells us that whether there is an entry or not. So if there is no entry, so what can happen is that if there is no entry in this table, so in this case we can actually check. In the previous case where we were not storing the tag, we were not sure which PC it exactly corresponded to. But in this case, since we are storing the tag, we know exactly which PC it kind of corresponds to. So if let's say we don't find an entry for a PC, what do? Well, we look at what is more probable. So since only 20% of the instructions are branches and 80% are not, we predict that it is not a branch. This of course can be wrong. Nothing much can be done. Why does an IST work? Well, the reason it works is mainly because most pieces of code exhibit temporal locality. That is that they keep on executing the same instruction over and over again. And when do we see that? Well, we see them in loops. And as I said, a program spends most of its time, roughly 90% of its time, in loops, right? Different kinds of loops. For loops, while loops, all kinds of loops, but the same instructions keep getting executed over and over again. And because of temporal locality, we capture a small region of the program, and if that is stored well in the IST, using the least significant bits, we can predict with reasonably good accuracy for we can predict the branch type with a reasonably good accuracy, right? So this is just the second statement is just repeating the first part, that we have a lot of loops in the program, and this is why our IST using the LSB bits works. Now let's move to the next problem, which is predicting the branch outcome. So predicting the branch outcome will, of course, this is built on similar principles. We will essentially extend the IST. So we'll extend the IST to create similar predictors, essentially similar principles, right? Built on similar principles. And these branch predictors will incorporate many more effects. Along with temporal locality, they will incorporate many more artifacts, aspects of the way that programs are typically written. So this will be covered in the next lecture of this lecture series.